to model turbulence effect.
Okay. So last time we introduced the different turbulence models, and we said that more we add equations, we can have a better prediction of turbulence effects. But of course, the analysis will be much more complicated. This is why from experiments and from a lot of practice, we were able to recommend which turbulence model to use depending on the application we have. Okay, and as we said, we started first by the one equation model, and we said, if you remember, that when we did the averaging of the Reynolds stress of the Navier-Stokes equation, we have a new parameter that will be added, a new term related to the fluctuation of velocity. And then to be able to model turbulence, these fluctuations, so we have terms like u prime I, u prime j bar, and we need to model this term. This is why we started first by a first approximation relating this turbulence to the eddy viscosity. So the first range of models is called eddy viscosity models, where we just define an equation, an additional equation, to relate, if you want, the stresses to a characteristic, which is the eddy viscosity of the flow. And then we need to solve an additional equation to the system of Navier-Stokes to predict turbulence. This is why we call it one equation model. Now, also, we have seen that this technique represents some limitations. It was good in certain applications, but in many applications, it performed in a poor way. This is why we developed other models. We started last time to talk about the two equation model concerning when we say K and epsilon. K is the turbulent kinetic energy. So it's the kinetic energy calculated function of the turbulence of fluctuations of the velocity field. You have the dissipation rate. As you remember, when we talked about turbulence, we have dissipation of energy. So we go from a larger scale to smaller scales. And we'll see that in K epsilon, we have several types, because what we do is just we do some modification in the equation. The idea is that whenever we want to treat turbulence, we add an equation for K, let's say, and we add an equation for epsilon. And as I told you, these equations are empirical. We do experiments in order to get empirical relations relating our turbulent variables. And we need then constants. We need, in this differential equation of K and epsilon, we need constants. These constants are determined empirically, and we can modify the form of the equation to, if you want to tackle other applications. And we will see, for example, that some standard K epsilon will perform in a good way in certain applications, while we have seen deficiency in other applications. So we modified the equation in order to be able to model a wide variety of turbulence in an accurate way. And now we'll come up with recommendations in this chapter. In which case do I use standard K epsilon? In which case I use the renormalized group K epsilon? And in which cases I use the realisable K epsilon? We'll also talk in brief about other models like standard K epsilon, SSTK, standard K omega, and SSTK omega. And as we move down with this chart, we have an increase of complexity in turbulence modeling, and then the computational time will increase. So of course, it's good to have better accuracy, but also the computational time is very important, because we need, any CFD simulation will take hours. So if you will be able to give an accurate result with a smaller time, then you will gain a lot of computational time and cost. So as we discussed before, the first model is Spallard-Almaras model. And as we said, it consists on introducing a transport equation for the eddy viscosity. Okay, so it is a category of eddy viscosity models. Now, from experience, we have seen that this model is mainly convenient for aerodynamic or turbomachinery applications with melt separation, such as supersonic, transonic flows over airfoils, boundary layer flows. So whenever you have an application related to this field, this model will perform well. This system also, this model embodies a relatively new class of one equation models where it's not necessary to calculate a length scale related to the local shear layer thickness. Well, as I told you, I know these ideas are complex. I just want you to know an overview of the models, and each one can be used in which application, because it's really complex to understand if you want their equations and how we modify them. And the researchers took a lot of time to be able to come up with these models. So they are very complex models, but we just should have an idea about that. For example, in Spallard-Almaras model, we are adding one equation for the modified eddy viscosity, and we should know that it's applicable for such problems. So if we have in CFD application, if your project is related somewhat to development of boundary layer or to aerodynamic or turbomachinery applications, then this model will perform in a good way. Now, as we said, so this model is designed specifically for aerospace applications involving wall-bounded flows. So it will perform well for wall-bounded flows application. And it has been to give good result for boundary layers subjected to adverse pressure gradient, and it gained popularity for turbomachinery applications. Now, concerning the limitations of Spallard-Almaras model, is that we cannot claim that it can be used for different types of complex engineering flows. We just suggest to use it for the following applications. And it cannot be relied upon to predict the decay of homogeneous isotropic turbulence. So if you have anisotropic or non-homogeneous turbulence, this model will not perform well. This is why we developed other models, other turbulence models. To start with, for the two equation models, as the name indicates, you have K epsilon. K stands for the turbulent kinetic energy, and epsilon for the dissipation rate of energy. So in this model, we are introducing two new variables, K and epsilon, and we need to write equations to assess how they change with time, okay, or how they change with time and space. So we need to get additional relations. So for example, here you can see that this equation represents the differential equation for epsilon. And as you can see, it's related to the eddy viscosity, it's related to the turbulent kinetic energy, and it involves constants. And as I told you, these constants are derived empirically. So it's not a pure mathematical relation. It's a relation developed based on observations and experiments. And then, as you can see, our different turbulent parameters are related through equations. So we have that the dissipation rate can be related to the turbulent kinetic energy, knowing the turbulence length scale. And also we can relate the eddy viscosity to K and to the turbulent length scale. So in this way, we have relations between mu t, K, and epsilon, which will close our system of equations. So we need to add two new equations if you want, two differential equations with some relations between our parameters. This is why we call it two equation model, K epsilon. Now, concerning the K epsilon model, we have, as we said, several types. We have the standard one, the renormalized group K epsilon, and the realizable K epsilon model. We'll discuss in brief the application of each of these models. To start with, The standard K epsilon is the most widely used engineering turbulence model for industrial applications. The model parameters of this of K epsilon, standard K epsilon, are calibrated by using data from a number of benchmark experiments. So as we mentioned before, these constants involved in the differential equations are determined experimentally. So let's say we performed several experiments on typical engineering problems like pipe flow, flat plate, to come up with these constants. This model was shown to be robust and reasonably accurate for a wide range of applications. It contains submodels for compressibility effects, buoyancy effects, if you want to model combustion. So this system presents, if you want, better accuracy than the first one in many engineering applications. But also it presents limitations. First, it was shown that this model performs poorly for flows with larger pressure gradient. So whenever you have large pressure gradient, it will not work very well. This is why if you have an application with large pressure gradient, you will not use the standard K epsilon model. When you have strong separation of flows also, it will not be accurate. In addition, if you have highly swirling component and large streamline curvature, the standard K epsilon model is not recommended to be used. In addition, it was shown to be inaccurate in prediction of the spreading rate of round jets. So if you have round jets in your problem, like the problem, if you remember, of personalized ventilation we talked about together, you have a round jet from the ceiling. It's not advised then to use this model. We'll see what are the models that are suggested in such cases. Plus, we have seen that production of K is excessive in regions with large strain rate. So whenever, for example, you are close to a stagnation point, this model will not give you the accurate physics taking place there, and it will result in very inaccurate model predictions. So whenever you have one of these limiting conditions, do not use the standard K epsilon model. Now, we said that we have other groups of K epsilon model. The second one is the realizable K epsilon model. Sorry. In this model, we have that we will modify the, if you want, the standard K epsilon equations to have better prediction and to overcome limitations of the standard K epsilon model. So first, the dissipation rate epsilon equation in this model is derived from the mean square vorticity fluctuation. So we took into account the vorticity fluctuation, which will help us into tackling more complex situations that the standard K epsilon model was not able to go over. So this is the main difference between realizable and standard K epsilon. So in this case, several realizability conditions are enforced for Reynolds stresses. And the advantages of this is that first, we can accurately predict the spreading rate of both planar and round jets. So whenever you have a round jet, it's better to use the realizable K epsilon. Also, it's likely to provide superior performance for flows involving rotation, boundary layers under strong pressure, adverse pressure gradient, separation, and recirculation. So we were able to overcome the main limitation of the standard K epsilon model by considering the effect of vorticity fluctuation. Now, concerning the renormalized group K epsilon, it's in this model, the constants in the K epsilon equations are derived analytically using a renormalization group theory. So this is a theory which will help us into deriving the coefficients of the equation instead of finding the equations from empirical relations and experimental data. And due to this, the dissipation rate equation will be modified. It was shown that the renormalized group K epsilon performs better than standard K epsilon for more complex shear flows. So whenever you have complex shear applications, it's suggested to use the renormalized group and the flows with high strain rates, swirl effects, and separation. So depending on the application you have, you can select the, and sometimes we can do comparison. And if you have a problem, You can compare the different models by simulation. And if you have, let's say, experimental data or literature data, you can compare with to know which one of these turbulent models will perform in a better way. Now, we move to other type of modeling. So we are still with, if you want, the two equation model, but now we introduce a new variable, which is omega. Okay, so omega will be, we will see that it's also related to epsilon. Okay, but in a certain modified way. So for instance, we can say that omega constitutes the specific turbulence dissipation rate. So it's the rate at which turbulence kinetic energy is converted into thermal internal energy per unit volume and time. And this omega is related to epsilon through an equation. So you have omega is epsilon over k. Okay, so times a certain coefficient, and this coefficient is a model constant that also can be determined empirically. And it was shown that standard K epsilon K omega model are a robust low Reynolds number formulation down to the viscous sublayer. So it performed, it shows good performance in low Reynolds number zones. And we have several submodels options for K omega. It can include compressibility effects, transitional flows, and shear flow correction. In addition, it showed improved behavior under adverse pressure gradient. Plus, it is more sensitive to the free stream conditions. So whenever you have a free stream application and you are interested in low Reynolds number regions, you can use standard K omega model. And this model is widely adopted in aerospace and turbomachinery communities. So we have seen until now that in aerospace and turbomachinery, two main models are used, the eddy viscosity models and the standard K omega model. Now, we have also what we call the shear stress transport K omega model. This model uses a blending function to gradually do the transition from the standard K omega model near the wall to high Reynolds number version of the K epsilon model in the outer portion of the boundary layer. So you know that in general, in any problem, sometimes you have combination. You have zones of low Reynolds numbers and zones of high Reynolds numbers. So you cannot, so in this case, you will not be able to select one of the options, and you don't want to select only K epsilon or only K omega because you have some transition zones, and you want to have a model that can predict the transition from low Reynolds numbers to high Reynolds numbers. This is the case of shear stress transport K omega model. This model, if you want, will introduce a function that will gradually do the transition from the standard K epsilon model near the wall to a K epsilon model in the outer region. And therefore, it will combine the advantages of both models. This model will contain a modified turbulent viscosity formulation to account for the transport effects of the principal turbulent shear stresses. And generally, this model gives accurate prediction of the onset and the size of separation under adverse pressure gradient. So it represents some solution to the limitations of K epsilon model, the standard one. Now, so all of these models have a common purpose, is to model the Reynolds stresses, okay? And it is to model the effect of fluctuation of velocity on the different parameters. Now here we are summarizing the limitation and weaknesses of eddy viscosity models. So first, whenever we use eddy viscosity models, we have linear algebraic stress-strain relationship, resulting in poor performance where stress transport is important, including non-equilibrium flows, separation, and reattaching flows. If you go back, if you want, to main idea of eddy viscosity models. In eddy viscosity models, we related the stress component, the Reynolds stress component, to the stress strain by a proportionality constant, which is the eddy viscosity. This model shown good performance in some applications, but as we said before, it represented poor performance in case of separation, in case of reattaching flows, etc. So this model shown an inability to account for extra strain due to streamline curvature, rotational effect, and highly skewed flows. What we mean by this, highly unhomogeneous flows. Also, it presented poor performance where turbulence is highly anisotropic. So whenever we have a high anisotropy, then you should go to other models than the eddy viscosity model. So in order to avoid these shortcomings of the eddy viscosity model, transport equation for the 6 distinct Reynolds stress components. So if you remember, we defined last time the tensor of stresses. This tensor of stresses resulted from averaging the Navier-Stokes equation. So we can, if you want, enhance this performance by averaging the product of velocity fluctuation and Navier-Stokes equation. And then a turbulent dissipation rate equation will be needed. We have seen that Reynolds stress model is most suitable for highly anisotropic 3-dimensional flows, where the eddy viscosity model will perform poorly. But the computational time cost, of course, is higher because you are moving from one equation to solve for turbulence effect to a higher number of equations. But of course, you will gain accuracy when doing this. Now, we know that the wall region is a very important region, and it should be modeled accurately, because in this region you have transition from zones, from layer to other. You know that whenever you have the development of a boundary layer, we have first what we call a viscous sublayer. In this viscous sublayer, the viscous effects are dominant. Okay. So always from observation, you have a dominant viscous effect because of the non-slip condition. Okay, so from fluids, you know that near the wall we have the non-slip condition, and then we force the flow to have a zero velocity if the wall is fixed. And then due to viscous effect, we have a transition from zero velocity to larger velocity. Now, as we go far away from the wall, the viscosity effect will be reduced. And then we have it like a transition zone called the buffer layer or blending region, where we have transition from viscous layer to fully turbulent region. And at the end, when we are far enough from the wall, then we have a fully turbulent region. Because of these different layers, modeling the flow behavior near walls is really challenging. It presents several challenges. And to be able to overcome this, we should come up with models able to consider the 3 different regions. Okay. Now, what is the idea here? If we want to, by computational equations, to model this, then we need to perform very, if you want, very thin size or very small size near the wall. And sometimes decreasing a lot the size can lead also to problems, okay? Because you will have also to have good transition from small size to large size, and then you need a lot of elements to do this, okay? This is why to predict accurately what is happening near the wall without having to increase a lot the computational time and the number of elements, we come up with some models that will take into account the different phenomena taking place near a wall. And these models are developed, of course, also empirically. And what we do is, for example, this is a very important example to show you the importance of the chapter of dimensionless analysis. if you remember, we introduced this chapter and we said that this chapter will allow us to come up with charts and use them for general cases. But because we are introducing dimensionless parameters, okay? So here we can see an example of this. So in this problem, we say, what are the important parameters we have? We want to see how the velocity of the flow U is affected by the shear stresses near the wall, okay? Because, and the viscous effect. So we can define, for example, the parameters of interest are U, the velocity of the flow. We have the shear stress, of course, because the shear stress is related to viscous effects and will lead to gradual transition of the velocity profile in the viscous sublayer. So we have tau near the wall. We have also, of course, whenever you have a flow, the important parameters that will be induced, of course, will be rho. You can talk about dynamic viscosity or kinematic. It's equivalent because they are related to each other. Okay, so you know that mu is equal to rho times the dynamic viscosity is rho times the kinematic viscosity. So as two variables, you can take or rho and mu as the dynamic one, or rho and the kinematic viscosity. And of course, here, since you are interested in the effect of the distance from the wall, so you want to see how the distance from the wall will affect the performance of the flow. So another variable of interest is y. Okay, so you say, I have the following parameters, okay? And I want to come up with dimensionless numbers that will allow me to model the behavior of velocity of a flow in a simple way, okay? So the first step you do is to say, let me determine what are my groups, what are my the different groups I have, and then once I determine what are my groups of interest, I can, if you want, draw a general graph that can be used for any application. So I perform the dimensional analysis, okay? And I come up with, let's say, groups. So here you can easily, you know already how to do the dimensionless analysis. You can easily do this practice here to say, let me find what are my groups. And you will find mainly here two main groups, okay? That are the following one. First, you have y plus. Y plus is a group related to y. It's related to, if you want, the distance from the wall. When we say just y, the unit is meter. So we need to come up with a group related to y. If you do the analysis, you will see that your group is of the following form. It's y times radical shear over rho divided by mu. So this is my first group of interest. I will call it y plus. This is called the y plus value. The y plus value is a group related to the distance from the wall. Okay, so as I go far from the wall, I can identify different regions: the viscous sublayer region, the buffer layer or blending region, and the fully turbulent region. And we'll see that from our experiment, we'll see that mainly the viscous sublayer region is limited to y plus values below 5. And between 5 and 60, we have like the transition zone, which have its own equation. And finally, okay, in the fully turbulent region, we can come up with fitting techniques to relate, if you want, the velocity variation with the distance from the wall. So the first parameter is y plus. And the second group, so here you can demonstrate that you have two main groups. The first group is y plus, and the second group is u plus, where u plus is related to is following. It's the velocity of the flow over radical of tau over rho. Okay, and we call this parameter, because we observe this parameter in both in y plus and in u plus, we defined a new parameter called the friction velocity. This is called the friction velocity. The friction velocity is related to shear effect. It's defined as a radical of shear over rho. Okay, so when we perform, if you want here the dimensionless analysis, we'll come up with 3 independent variables. The 3 independent variables are tau, rho, and mu. Okay, and the two groups, to form the two groups here, your two groups will be formed by combining first, the first group, group 1, pi 1, is formed by combining y with these parameters. And from your analysis, you will get, as we said, you will observe the group will be y times this term, which is radical tau over rho over mu. And the second group you will come up with is for the velocity. So pi 2 is obtained by combining the velocity of the flow u with the three independent variables tau, rho, and mu. And you will find out that the group that you will get is u plus equal to u over radical tau over rho. And since we observed radical tau over rho in the two groups, we decided to name this component the friction velocity, ut. Okay, and in some books they refer for it as u star, like this. So u star is the friction velocity is related to the shear at wall level. And then we do experiments. In this experiment, we vary the first group, which is y plus, and we measure experimentally the group u plus, and then we can come up with a graph. And this graph will be a general graph because it was performed based on dimensionless analysis. Okay, so you can use it. You can use it in any case, okay, where you have flow near a wall. And then you can identify a general rule for the development of your layers and say that I have the viscous sublayer in region of y plus smaller than 5. My buffer layer will be between 5 and 60, and my turbulent region will be above 60. Now, whenever you have this graph, this will help you into modeling the flow behavior near the wall. Instead of doing it by computational fluid dynamics and dividing this part into very small elements, you can say, let me use this graph to come up with empirical relation between how u is varying with y in the viscous sublayer. So here, for example, okay, you can see that from this profile, you can come up with fitting techniques to get near in the sub-viscous layer, what is y plus? So this is the first function, function 1 of y plus, u plus function of y plus. By fitting technique, you get an empirical relation here. Now you can see that in the buffer region, you have like a transition zone. So you have a change in behavior. This change in behavior will lead to a new function. So in the buffer layer, you have u plus is another function of y plus. So f2 function of y plus. And you can see that as I go far, if you want mainly in the buffer region here, you can identify like a profile. And after it, just after it, when you start the fully turbulent region, you have change in profile. You start to see like a straight line variation. So you have like a constant slope of variation between u plus and y plus. So nearly you can say that when I'm far away from the wall in turbulent region, I can say that I can relate u plus as a linear function of y plus. Okay, And then when I am very far, I can see another behavior also that can be computed through an equation. So from here, you can say that by observing this graph, I can come up with empirical relations that will allow me to model the flow behavior within the boundary layer without having to resolve it into very small size. Okay, so uh, and once you develop these empirical relations, you can implement them to CFD. This is why, if you remember, when we were discussing in the CFD lab the different options in ANSYS Fluent, if you go back to the window of turbulence, when you select K epsilon, for example, you have also with K epsilon below it, you can select the option of enhanced wall treatment. Whenever you select enhanced wall treatment, then ANSYS will implement all of these models to take into account the effect of flow development near the wall. Okay, so this dimensionless velocity profile is plotted in the near wall coordinates, and the linear section in the semi-log plot is called the universal law of the wall layer, or log law layer for equilibrium turbulent boundary layers. Now, why we need to enhance this to perform the near wall treatment? Because in the near wall region, the turbulent boundary layer is very thin, and the solution gradients are very high. But accurate calculations in the near wall region are paramount to the success of the simulation. So as I told you, it's very difficult to resolve. When we say to resolve, means to have enough element in this region to be able to capture the different physics taking place. And because it's challenging and because it's adding a lot of computational time, plus we have the problem of transition of size from the wall to the region after, it's important to implement these empirical relations in CFD in order to have an idea about what is happening near the wall without having to increase a lot the computational time. So instead of using a very fine mesh to resolve this region, which is very costly for industrial CFD application, what we can do then is, as I told you, to implement these empirical relations developed into CFD. So for equilibrium turbulent boundary layer, we can use the universal law of the wall, which was developed in this graph, in order to solve this problem. So in this way, velocity profile and wall shear stress obtained from the log law will be used to set the boundary values of stresses for the wall adjacent cells. And then the equilibrium assumption can be used to set boundary conditions for the turbulent kinetic energy, dissipation rate, or specific dissipation rate. Now, non-equilibrium wall function method attempts to improve the results for flow with higher pressure gradient, separation, reattachment, and stagnation. And even this law can be modified whenever you have new applications showing that it's not performing. And this, for example, graph was developed under certain conditions. Okay, if we have separation, if we have large pressure gradients, it might not work very well. This is why we need to come up with another graph under similar conditions. You know that to be able to extrapolate these results, we need to have common applications. Whenever you have larger pressure gradients or you have separation zones, you can come up with new or modified laws in order to account for these effects. So similar log laws are also constructed in order to take into account other cases like energy and species equation. And the benefit of wall functions is that they will allow to use a relatively coarse mesh in the near wall region while giving good prediction of the behavior of flow near the wall. Now we'll see here, for example, how near wall mesh treatment can enhance the prediction. So for example, if I take standard and non-equilibrium wall functions, then the wall adjacent cell should have y plus value between 30 and 300 to 500. and the mesh expansion ratio should be small enough